Good day everybody, we got this beautiful integral 0 to 1 arctan of root of x squared positive 2 divided by root of x squared positive 2 times x squared positive 1 times dx. Now this is popularly called as the Ahmed's integral. Let's get started. So first what I wish to do is I would like to apply the Leibniz technique of integration. You can also call it as Feynman's technique, because it's the mathematician Feynman who had popularized this, but the original creator of this technique is Leibniz, and it is imperative that I mention you that important fact. So having mentioned this, let me go up and define a function. So I would like to define this as I of t is equal to integral 0 to 1 arc tan of root of x squared positive 2 divided by square root of x squared positive 2 times x squared positive 1. Now since I have got a t here, I would like to place a t there, and you are free to place t anywhere because you are actually defining the function, but I am placing the t inside, and this has to carry the differential operator dx. Now we are interested in knowing the value we want when t is equal to 1. So that would mean I of 1 is our objective. Now having obtained or having set this objective, it is imperative that we establish certain boundary conditions, and for me I would like to know when t is heading to or tending towards infinity. So that would mean this would be acting as a boundary condition for me. So I need to know what happens to the function which I have defined I of t when t is heading to infinity. Now in this case clearly you can see that t is the only variable that we have utilized in defining the function. So arc tan of t. Now what is arc tan of t? If I were to write this as arc tan of t, this is nothing but tan inverse of t. Now t is heading to infinity, so tan inverse of infinity is going to be pi over 2. So this is the all important fact that we will be utilizing. So that would give us pi over 2 times, then the numerator is already taken care of, it has resulted in pi over 2. So just write the other quantity. So we got dx over root of x squared positive 2 times x squared positive 1. Now on the left hand side you can suitably represent it as I of infinity, so that you can have a fairly good value. Now what I wish to do is I would like to evaluate this first and find out what happens when t is heading to infinity. So let's do that. So I would like to consider the integral 0 to 1 dx divided by root of x squared positive 2 times x squared positive 1. So I need to know the value. So foremost what I wish to do is I would like to take x is equal to tan theta, right? So if I take x is equal to tan theta, I can get the value for dx. So dx is going to be equal to secant squared theta times d theta. So that's fine. But when x is equal to 0, my theta will be equal to 0. When x is equal to 1, my theta will be equal to pi over 4. You can substitute here. When x is equal to 0, tan inverse of 0 will give you 0. When x is equal to 1, tan inverse of 1 will give you pi over 4. So having got that, let me substitute that value. So 0 to pi over 4, and my dx is secant squared theta d theta divided by root of my x is tan squared theta, and I have to have a 2 there, times x is tan squared theta plus 1. Now we can utilize the trigonometric identity secant square theta negative tan square theta, which is equal to 1. So from here secant square theta is equal to 1 plus tan square theta. So this is rewritten as 0 to pi over 4 1 plus tan square theta divided by root of tan square theta plus 2 times tan square theta plus 1. Now tan square theta plus 1 and tan square theta plus 1 can be cancelled, giving me integral 0 to pi over 4 d theta divided by, now tan theta is sin theta divided by cos theta, tan square theta is sin square theta over cos square theta. So by that you got root of sin square theta divided by cos square theta plus 2, which I can rewrite it as root of sin square theta plus 2 times cos square theta. There is a root of cos square theta in the denominator. You flip that, you get 0 to pi over 4. Root of cos square theta becomes cos theta times d theta divided by root of sin square theta plus 2 times cos square theta. But cos square theta is 1 negative sin square theta. Right, you can utilize that, but what I want to do is, before I could utilize this, excuse me, I would like to write 2 times cos square theta as cos square theta plus cos square theta. So two important identities or representation would be utilized here. So this is equal to 0 to pi over 4 cos theta divided by root of sin square theta. As I mentioned to you, 2 cos square theta is going to be written as cos square theta plus cos square theta. This is equal to integral 0 to pi over 4 cos theta d theta divided by sin squared plus cos squared is 1. So I got a 1 there, and there is a cos squared there. I'm going to write cos squared as 1 negative sin squared, and now you got 1 added with 1. So that's 0 over pi over 4, and you got cos theta d theta divided by root of 2 negative sin square theta. Now I would like to make a substitution. Let sin theta be equal to root of 2 times some sin u, and if I were to differentiate this, I would get cos theta d theta is equal to root of 2 times cos u du, right? So we need to know what is the value, how theta is taking the values and influencing the variable u. So if you were to take theta is equal to 0, my u is going to be equal to 0, but when I take theta is equal to pi over 4, I get sin pi over 4, that's 1 over root 2. So my u would be, let me show you that. This is 1 over root 2 times 1 over root 2. So u is going to be sine inverse of 1 over 2. But what is sine inverse of 1 over 2? That's going to be 30 degrees. Right, but what is 30 degree? 30 degrees is nothing but pi over 6. So u is pi over 6. So this is equal to integral 0 to pi over 6 cos theta d theta is root of 2 times cos u du divided by my, this is going to be 2 times sin u, that's going to be, let me write that, 2 negative 2 times sin square u, there's a root there, so if I were to take the root out, so this is going to be root of 2, the 2 goes out, so it's going to be root of 2 integral cos u du divided by, this is 1 negative sin squared u, that's going to be cos squared u, root of cos squared u is cos u, right? So cos u can be cancelled, root 2 can be cancelled, you get 0 to pi over 6, this is what you've got. So integral du, when you integrate du, what do you get? You get u. So let me write that down. So this is equal to u, the limits are 0 to pi over 6, you substitute the upper limit, that only carries a value, so you're getting pi over 6, right? This is the all important value, pi over 6. So you come over here, I have evaluated this integral. right? But what is this integral? This integral is nothing but part of this integral. So you get pi over 2 times pi over 6 is nothing but pi squared divided by 2 into 6, that's going to be 12. So you're getting pi squared over 12. This is I infinity. So we got the boundary condition. So now we need to move up to evaluate the integral, right? I of t. So let's do that. Since I've got the page exhausted, I need to go to the new page. Okay, so let me rewrite the integral. So we have defined this function I of t to be equal to integral 0 to 1 arc tan of t times root of x squared positive 2 divided by root of x squared positive 2 times 1 positive x squared times dx. So this is what we started with. Now what I wish to do is I would like to operate on both sides d over dt. So that's the first step. Now this is the process, right? This is the process that Leibniz gave for integrating complex integrals like this. Now I would also like to state the condition that we have got. So we have got I infinity to be equal to pi squared over 12. So this has already been evaluated. Now let me place d over dt integral 0 to 1 arc tan of t times root of x squared positive 2 divided by root of x squared positive 2 times 1 positive x squared times dx. Now d over dt is a total differential. Now I would like to pull this inside. Now that is only possible if the quantity that you see here in the numerator is bounded. Now clearly arctan is bounded. So because of the fact that the quantity is bounded, I can push in d over dt. So if I were to bring the total differential inside the integral, clearly you can see that there are two variables t and x, and I will have to represent the total differential as partial derivative dou over dou t of arc tan of t times root of x squared positive 2 divided by root of x squared positive 2 times 1 positive x squared, right, and the differential operator dx. Now you will have to differentiate tan inverse. Arc is nothing but tan inverse, right? So the differential has to be performed for tan inverse of t. So what is tan inverse of t? You have to know this. So if you want to differentiate d over dt of tan inverse of t, what do you get? Derivative of tan inverse of t is nothing but 1 over 1 positive t squared, right? This is the value. So I need to apply this concept over here. And luckily for us, we got only t there. So that is easily manageable. So having said that, let me go and differentiate that. So this has got no part to play. So let me write that part out. So root of x squared positive 2 times 1 positive x squared. Now I need to just perform the total derivative, or I should say the partial differentiation dou over dou t of tan inverse, I prefer to write it like this, tan inverse of t times root of x squared positive 2, right? So this is what we are going to be performing now. However, you got the integration 0 to 1 and you got the operator dx. So if I were to differentiate this, this is going to give me 1 over 1 positive. This is my t, so it's going to be t times root of x squared positive 2 raised to the power of 2 times the differentiation of this entire quantity. See, the differentiation of this entire quantity, t is the variable in consideration, so other things are all constant, so all we get is just root of x squared positive 2. Right, so that is the outcome that we would be having when we differentiate tan inverse of t. And let me place this dx and the integral sign with the limits followed by root of x squared positive 2 times 1 positive x squared. Now clearly you can see here root of x squared positive 2, root of x squared positive 2 can be cancelled, right? And what are you left with? You're left with integral dx divided by this is going to give me t squared followed by x squared positive 2. So let me write that quantity, 1 positive t squared times x squared positive 2, that's one quantity, multiplied with 1 positive x squared. So this is what we've got. So now what I wish to do is, I would like to apply partial fractions, because without the application of partial fractions we wouldn't be able to separate them. So how are we going to apply partial fractions? Foremost, let me rewrite this 0 to 1 dx divided by this quantity. Let me distribute this. So this is going to be 1 positive t squared x squared positive 2 times t squared times 1 positive x squared. So I'm going to consider this quantity 1 over 1 positive t squared x squared positive 2 times t squared times 1 positive x squared. Let me rewrite this as a over, the variables are all degree 2, so you don't have to worry about the form of the partial fraction, so you can just outrightly state them as follows. So t squared x squared positive 2 times t squared positive b over 1 positive x squared. So this is what you've got. So having got that, we need to set up the values. Now the variable in question is x, so t is just a constant. So what I wish to do is, first I would like to cross multiply and rewrite this as 1 is equal to a times 1 positive x squared plus b times 1 positive t squared x squared positive 2 times t squared. So this is what we've got. So now what we will do is, we will have to eliminate one variable at a time. So if I were to take x squared is equal to negative 1, this is eliminated, x squared is negative 1, you get 1 negative t squared. Over here it's going to be b times 1 negative t squared added with 2 t squared would give us 1 positive t squared. You got a 1 here. This is 0 is equal to 1. So therefore b is equal to 1 over 1 positive t squared. So that's the value for b. Now you can take another value. So x squared is equal to 0. If x squared is equal to 0, this is 0. Right? This is 0. So you get 1 is equal to a plus b times of 1 positive 2t squared. Now clearly you can place in the value of b here. So if I were to place the value of b, then this would be equal to 1 over 1 positive t squared times 1 positive 2 times t squared, right? So I need to get the value of a, so push everything to the other side. So that's going to be 1 negative of 1 positive 2 times t squared divided by 1 positive t squared. This is what we have got. So now you take the LCM, and 1 positive t squared is the LCM. So this is going to be 1 positive t squared, negative 1, negative 2 times t squared, which is equal to, so clearly negative 1, positive 1 goes away, and then you got negative t squared divided by 1 positive t squared. So this is the value you have got. You got the value for A, you got the value for B. So now you've got to substitute. I've exhausted the page. Let me move to the next one. Now this is what we actually started with, and we've got the value of A to be as negative t squared divided by 1 positive t squared, and the B value is 1 over 1 positive t squared. This is what we've got. Now this is actually the integral. So let me write the integral down. So on the left we add I dash of t, right, because we applied the total differential. So this is going to be I dash of t is equal to 0 to 1. This is dx of 1 positive t squared x squared positive 2 times t squared times 1 positive x squared. This is disintegrated into the partial fraction. So integral, in place of A I will substitute negative t squared divided by 1 positive t squared times 1 positive t squared x squared positive 2 times t squared times dx, and in place of B has already got 1 over 1 positive x squared. So let me start by writing 1 over 1 positive t squared times dx divided by 1 positive x squared. The limits are 0 to 1. The limits are 0 to 1. Right? So now we need to handle this. So let me just first simplify this. So I will start off by considering t squared divided by, now 1 positive t squared, this has got nothing to do. So in fact I could have taken this t squared out. Anyway, let me just place this t squared out here, and then you got 1 positive t squared x squared positive 2t squared. Now what I wish to do is I would like to first give a form to this quantity. So let me write this as t squared over 1 positive t squared integral dx divided by, and if I were to take t squared out, right, then that would be, I can take a t squared out. If I were to take a t squared out, this is going to be x squared positive, a t squared goes off, so this is going to be a 2 there and a 1 over t squared. So this is the form, right? So t squared can be cancelled, giving me integral dx over, let me write that x squared out, and I got a 2 positive 1 over t squared. Now this 2 positive 1 over t squared, I wish to write it with t as a quantity. So it's going to be 2 times t squared plus 1 divided by t squared. So this is what I've got. And is there anything else we can do? Is there anything else? Okay, so having got this, let me move on. Now to integrate this, let me draw your attention to this most popular formula. Integral dx over x squared positive a squared is nothing but 1 over a tan inverse of x over a, right? So I would like to apply that formula here. So if I were to apply that formula here, this is going to be 1 over a, so it's going to be 1 over a is root of 2 times t squared plus 1 divided by root of t squared is t times tan inverse of x. My x is over here divided by a. It's going to be root of 2 times t squared plus 1 divided by t. right? The limits are 0 to 1. Now, since we are dealing only with x, that's the reason I'm placing the parenthesis and the limits at the head here. So this can be rewritten as, you flip it, t over root of 2 times t squared plus 1. Now the upper limit is 1 and the lower limit is 0. The lower limit is not going to have any impact at all, but tan inverse of 1, that will definitely have an impact, right? So tan inverse of 1 would produce me what? Let me show you that. Tan inverse of 1 is equal to pi divided by 4. So we will have to utilize that, but to our, what would I say, the problem is not offering us just tan inverse of 1, but along with tan inverse, the functional variable, you got the constant. So if I were to flip that, this is going to be giving me, let me write that down here. So I've got that already here. So I will write one more statement here. Tan inverse of t times x divided by root of 2 times t squared plus 1. So this is what we have got. The limits are 0 to 1. So as I mentioned to you, if it was just x there, then things would have been much easier for us. But in this case, it is with t over root of 2 times t squared plus 1. So there isn't much for us to be happy about. So we will have to go through the fire. So t over 2 times t squared plus 1, and this is going to give me tan inverse of x is being substituted. So it's going to be t over root of 2 times t squared plus 1. Of course, I'm not worried about the lower limit. It is giving me 0. So all this has been obtained from considering this part of the integral. Okay. So what I have to do is, I will have to take this as sum 3 and then place these values and then start back again. So let me write that down. So 3 will now be rewritten with the new found values. So since I have not taken the negative sign, I need to cater to that. So therefore 3 is going to be I dash of t is equal to negative this quantity. So I have to place this quantity, right? But you can clearly see that there is a 1 over 1 plus t squared that is featuring. I have not taken that, I have just placed it, but I will have to place that value. So 1 over 1 positive t squared, and you got 1 over 1 positive t squared, right? That value has to be placed here. But because we are restricted with some space, I have not placed that value. So that value also occurs here. So if you were to place that value, it's going to be 1 over 1 positive t squared. So if you were to continue writing that 1 over 1 positive t squared, it would literally confuse everybody. So it's better that I just leave that out and then explain you. Now that I have finished with the explanation, it's time for me to fuse the value and then substitute back. So I got I dash of t to be equal to negative 1 over 1 positive t squared times this quantity. This quantity is t over root of 2 times t squared positive 1 times tan inverse of t over root of 2 times t squared plus 1. So this is the value followed by this value. You see this? Now I have not integrated that value. I need to integrate it. So 1 over 1 positive t squared times integral 0 to 1 dx over 1 positive x squared. Now things are a little bit easier here, because if you were to integrate this, what do you get when you integrate this? Let me show you. Integral 0 to 1 dx over 1 positive x squared. This is going to be 1 over a times tan inverse of x over a. The limits are 0 to 1. Now this is nothing but if you have to apply the upper limit, the lower limit is going to be 0. Now this is the beauty. Tan inverse of 1 is simple. What is tan inverse of 1? I already mentioned you here. Tan inverse of 1 is pi over 4. So this is going to give me pi over 4. So take this value of pi over 4 and place this. So rewriting, let me start to rewrite with the smallest quantity first. So that's going to be, not only that, it starts with a positive sign. So this is going to be pi over 4 times 1 over 1 positive t squared, right, negative this quantity t over 1 positive t squared times root of 2 times t squared plus 1 times tan inverse of t over root of 2 times t squared plus 1. Okay, so we have got a beautiful value here. On the left hand side it's I dash of t. Okay, now we need to get rid of the I dash of t, and that is got by integrating. So I'm going to integrate I dash of t times dt. Right, now you might be wondering what integral or what limits you are going to be placing here. Now as I mentioned to you at the start, we are interested when t is equal to 1, and we have already got the boundary condition when t is equal to infinity. Now this is why I got the boundary condition. Now without the boundary condition I wouldn't be able to place the limit. So I want 1 and I know infinity. What happens to the function when t is tending towards infinity? So that's the reason I'm placing 1 to infinity on the left hand side. So on the right hand side I need to integrate all of this. So this is going to be integral 1 to infinity, place pi over 4 outside. So since the integration is with reference to t, you can easily place dt divided by 1 positive t squared. This is easy. Now the complication part will come when you are integrating this one. So this is 1 to infinity t times tan inverse of t over root of 2 times t squared plus 1 times dt divided by 1 positive t squared times root of 2 times t squared plus 1. So we need to integrate this one, right? Now this, if you were to integrate this from fundamental theorem, you can clearly state this to be as upper limit, right? Because differential and integration, they get cancelled, they get neutralized, so giving us I infinity negative I of 1. So left hand side is already achieved, but now we need to obtain this part, right? So if you were to ask me how far have we finished, I would say we are just getting started. That's the best answer to give you, because this is another monster that has to be dealt with. So let me show you how to deal with it. So let me start from the previous page, which we had I of infinity negative I of 1 is equal to pi over 4 times 1 to infinity dt over 1 positive t squared negative integral 1 to infinity t over 1 positive t squared times root of 2 times t squared positive 1 times tan inverse of t over root of 2 times t squared positive 1 times dt, right? This is from the previous page. Now I can evaluate this. So let me consider integral 1 to infinity, there is a pi over 4 dt over 1 positive t squared. Now this is nothing but tan inverse of t. Limits are 1 to infinity, now which is nothing but pi over 4. Tan inverse of infinity is pi over 2. Tan inverse of 1 is pi over 4. This is pi over 4. LCM is 4. That would give me 2 pi negative pi, which is pi over 4 times pi over 4, which is nothing but pi squared over 16. So this value will go in here. Now we need to evaluate this. So foremost what I wish to do is, I will start off by consider this quantity. What is this quantity? Consider integral 1 to infinity t over 1 positive t squared times root of 2 times t squared positive 1 times tan inverse of t over root of 2 times t squared positive 1 times dt. So I will integrate this and then I will come back to the spot here and then I will substitute the values. I already have evaluated this. This is pi squared over 16, and then all I need to do is obtain the value of this. So I will place in the value of this along with this and then perform the simplification, and then I will obtain the value of I of 1. Make the following substitution. So what is that? Let me take t to be equal to 1 over t. So when t is equal to 1, we would have a new variable. Now instead of saying t is equal to 1, let me take t is equal to some p, because the signs get confused, right? So when t is equal to 1, my p will be equal to 1, and when t is equal to infinity, my p will be equal to 0, right? So I'm going to change from t variable to p variable. So this is going to be integral. When it is 1 1, when it is infinity, it is 0. So my t is 1 over p. So I substitute 1 over p there, divided by 1 over p. That's going to be p squared divided p squared plus 1 divided by p squared times root of 1 over p. That's going to be 2 plus p squared divided by p squared tan inverse of 1 over p. Now 1 over p, I just place 1 over p divided by, this is going to be root of 2 plus p squared, right? 2 plus p squared divided by p squared. So that p squared will be there, the root will flood all over. Now dt is negative 1 over p squared times dp. So negative 1 over p squared times dp. So that is the value that we have got. Okay, so now we need to place in some evaluation. So we need to evaluate certain quantities. So how are we going to do that? Now clearly this p squared, okay, now let me perform some simplifications. Okay, so when I flip that here, this is 1 to 0. If I were to flip that, that goes as numerator, so I will have a p there, because p squared and a p gets cancelled. I get a p there divided by p squared plus 1, and then this is going to be root of 2 positive p squared and divided by p. So if I were to flip that p there, that will become p squared over here, and then I get tan inverse of 1 over p, and I got a p squared here, so they get cancelled, giving me 1 over root of 2 plus p squared, and there is a negative 1 over p squared times dp. So this and this can be cancelled. Negative, I will flip the integral from 1 to 0 to 0 to 1, so that negative sign gets neutralized. So now I get 1 over p squared plus 1 times root of 2 positive p squared times tan inverse of 1 over root of 2 plus p squared. Now I would like to apply an identity. So tan inverse of x plus tan inverse of reciprocal of this x will be equal to pi over 2. So by that, tan inverse of root of 2 plus p squared plus tan inverse of 1 over root of 2 plus p squared is equal to pi over 2. So in place of this, I would like to apply tan inverse of 1 over, let me rewrite this, 1 over root of 2 plus p squared is equal to pi over 2 negative tan inverse of root of 2 plus p squared. So substitute that over here. So this is equal to 0 to 1 over p squared plus 1 times root of 2 positive p squared times pi over 2 negative tan inverse of root of 2 plus p square times the dp. So this can be rewritten as pi over 2 times integral 0 to 1 dp divided by p square plus 1 times root of 2 plus p square negative integral tan inverse of root of 2 plus p square divided by p square plus 1 times root of 2 plus p square times dp. So this is what we have got. Now what is the value for this? We know the value for this and we just evaluated this. Now I will have to turn back and show you that value. If not, you can just pause the video and you can see for yourself that we have already evaluated this particular quantity. If you remember, this is nothing but the boundary condition that we were looking for, and I will just substitute the value. So we can literally place this value. This is going to be pi squared over 12 negative this quantity. What is this? This is nothing but I of 1, right? We have defined this to be as I of t. Now if you are wondering how is it that we started with t and we are ending up with p, it doesn't matter. See, for example, you can simply make the substitution again back. So this is from 0 to 1. If I were to take p is equal to t, and this would be giving me dp is equal to dt, and still this is going to be giving us the same function that we started off. Place all these values and then complete the question. So on the left we got I of infinity negative I of 1 on over here. Now we need to take this and substitute back in the original part. The original part started with pi squared over 16 followed by the quantity that we just considered and evaluated. So this is going to be pi squared over 12 negative I of 1, right? But apparently there is a negative sign that is flowing, so this is going to be a positive sign here. We are on a new page, so let's make the simplification. Now I of infinity is pi squared divided by 12. I'm pushing this, so this is pi squared divided by 12. This is 1, and negative I of 1, and I'm bringing this negative positive I of 1, that will become negative I of 1. On this end I've already taken care of this. All that remains is pi squared divided by 16, right? So let me make this conduct the simplification here. So this is going to be 2 times of pi squared negative 2 times I of 1 is equal to pi squared over 16. So this is going to be 6. So pi squared over 6 negative 2 times I of 1 is equal to pi squared over 16. Now what I wish to do is I would have to conduct the simplification. So let me move this over that side. So negative 2 times I of 1 is equal to pi squared over 16 negative pi squared over 6. The LCM, if you were to take the LCM, I will take LCM as 6 are 36 3 and 96. So this will become 6 times pi squared negative 16 times pi squared, which is going to be negative 10 times pi squared divided by 96, and you got a negative 2I of 1. So negative positive, 2 divides here 5 times, so therefore I of 1 is equal to 5 pi squared divided by 96. So this is the solution for the question. Thank you everybody.